All right, testing. Oh, it looks like we're good. All right, good morning, everyone. Um, Welcome back to the stream. I have to apologize. I had a bit of a rough night last night. A good night, but it was very rough. So I'm a little bit hazy today. Um, but we're back. So what are we doing? So last time I talked about using creating more of a declarative kind of API for the user to um, specify their graphics pipeline to us. So specify their vertex buffers, their index buffers, and their shaders, and then subpasses and all that kind of stuff. And I talked about the idea of like deferring. So the user says, okay, here's a vertex buffer and this is the data. And like we take that information, but we maybe don't create that buffer straight away. We just give the user back like a handle. Um, and then later on, at a later point in time, when we have all of the vertex buffers, we can, do some efficiency things. So rather than making one allocation for each buffer, we can make one big allocation for all the buffers. Um, so that's the idea. I've been doing a lot of research and like trying to work on a few things on some draft branches um, since the last stream, just trying to figure out kind of where to go next. And I have to be honest, I'm not 100% sure still. So I did learn some things though that we'll just like take and start looking at today. But yeah, I'm not 100% sure of like exactly how I'm going to go. But we'll see. We'll see. So I hope everyone's good today, and thanks for watching. It's great to have some people back. Um, yeah, let's get started. So let's have a look at what we did last time. What was the last thing that we did? Commits. So the last thing we did was we used this acquire type everywhere. Let's have a look. Let's, let's not dox myself. Um, yeah, keep most of that. Acquire. Yes. Let's have a look at that. So this acquire type, it's part of the resource T package. Um, and yeah, please jump in if you have any questions or any direction you'd like to see the series head. Um, just jump on in. So this acquire type, uh, we create an acquire type using this function here. And it's just like bracket. So we've got a function or like a computation that'll acquire the resource, a computation to free the resource, and then we get an acquire back. And this is like an example of deferring. So we tell it how to acquire the resource, we tell it how to free the resource, but we don't actually acquire the resource. We just hand them back essentially this like data structure. And when they use a function called like with, then we allocate the resource for the duration of this function argument, and then we free it at the end. There's also a second way that you can use acquire. You can use allocate acquire, which essentially is using the resource T monad or the resource monad to allocate the resource, and then in the resource monad, we register a cleanup action to occur when the resource is run, the resource T monad is run. So yeah, we started using this everywhere because this gives us a little bit more flexibility about when we acquire resources. And we modified our examples to create and acquire type that includes all of our kind of initial resources like our shaders, our um, set layouts, command pool, vertex buffers, things that aren't going to change. Uh, yeah. So, what I want to start with today, raw util. So I'm going to create a new module that's going to hold this kind of encapsulate this idea of deferring resource creation. So where I first went with this is this presentation that I've been using a lot called Modern Mobile Rendering at HyperPipe. Um, and they talk about their sort of handle infrastructure. So here we go. Uh, Essentially, they just have arrays that hold data. So the user will be like, create this buffer for me. I'm not sure if they create the buffer at that time or not, but essentially they might store that data in this array and give the user back an index of like where in the array their data is. Um, and then things get more complicated, like they uh, keep track of generations to make sure that you're not trying to use a resource after it's been freed. Um, they split the pool into hot and cold data. And for us, this would look like the cold data essentially being like the parameters that we use to create um, like a texture, say. So like the width, the height, all these kind of things that are necessary to create a texture. But the hot data is the data that's actually needed when we're rendering that texture, which is just the VK texture handle. So this is where I went first, and I tried creating a pool and like handling out indexes and all that kind of stuff, and it just it felt difficult. And also, keeping this thread safe in Haskell involves using something like a mutable array, and it just didn't feel very functional, for lack of a better term. It just didn't feel like it flowed very well with the rest of the code base. It felt out of place. So I did some looking at like, okay, what are like handles um, in other kind of packages? Like if we have a look at, I think it's Postgres simple. Yeah, here we go. If we have a look at Postgres simple, I know they kind of use this idea of like a handle for the connection type. So I had a look at there. You can think of essentially this connection as a handle. And if you have a look here, this is the connection type. Um, they've got this idea of this connection handle, and it's an M bar. Um, and this kind of got me thinking, like we can just use an M bar as a handle. It's sort of like ah, how do I say this? It's like it is a handle. Like Haskell is like managing all that handle infrastructure for us. If we just put M var around whatever type we want, we can share it between threads. We can like have it be empty initially and then fill it up later so we can kind of defer the creation of the resource. Um, yeah, there's no kind of um, use after free issues. Yeah, so I just thought it might be a good start for us. Um, we're not maintaining indexes in array. We're not doing any of that. It's just working for us. So that is my first port of call. All right. So, oh, give me one sec. Sorry. Oh, okay. Sorry, just setting up the chat so I can see it while I code. Um, all right, so we've got this idea of a deferred type. Um, so this first argument is going to be the parameters that we will uh, record that will be used for creating the type. So this will be the buffer create info data structure. And the user will give us that. They'll tell us, okay, you know, this is how I want you to create this buffer. You know, here's some data. Here's the size of the buffer. Um, here's the vertex layout maybe. Um, and then we won't actually create that buffer, um, but we will give them back a handle to a buffer. And they think that they created a buffer, they can use it like that. Um, oh, sorry, I'm just getting a phone call. I think it's a plumber. Apologies, I'm just waiting on a call from a plumber. Got a bit of a leak in our bathroom, but it was just spam. Fun times. So yeah, we've got the initial creation part. That's the A, and then the B is going to be like the final type. Um, so the user will give us the A. Um, we're going to store a B, and that's going to be our type. So this is like using the more normal, the more familiar way of declaring this. That's the more familiar way of declaring this. And this is going to work out well for us because something else that happens is, um, let's say the user creates a render pass, and we give them back a handle to a render pass. Um, we have a slight issue in that, like the first time we create the render pass, great, we've created the render pass, that's great. But every time the swap chain's resized, we need to recreate the render pass. And so this kind of gives us like a transparent, the user can just use the handle and the data that is actually backing up that handle is going to change over time. And like from the user's perspective, it doesn't matter. Um, so, and reason I'm using this GADT syntax is because we're going to have some more interesting types make it into this definition uh, soon. So, cool. So how do we create one of these? Let's give the user a function to give us an A, then we give them back a deferred A. New empty env? Is that what it's called? New empty env. So we're going to create the env initially empty. Cool, and we'll just lift IO this. And import all the things. Cool. And then, what should we call this? let's just call it eval for now. So, if we get given a way to create the B from the A, then go ahead and do that and return the result. So, this look like I'm gonna have to check if the M var is empty or not. So, what have we got for that? So, modify M var. Let's see. Yeah, so modify M var takes the M var. So it'll wait if it's empty, which will be no good for us. So for now, let's assume it's empty and we'll work out the issues later. So, if we try and take the M var, just wondering if I can do this better with a TM var. Because we have a TM var, I could do something like try take TM var. This will be an atomic block. Um, so if the M var is empty, the TM var is empty, um, then we take the TM var. Let's just add this as a import. So the issue is that, let's say we just did this with a normal M bar. We'd try take the M bar, it'd be like maybe a B, and then we'd be like case nothing, case MB of nothing, and then we'd be like, okay, so the M bar was empty. Let's evaluate our function and then put it in the M bar. Which seems simple enough. And then if it's not empty, we'd like modify the M bar, and then we take that. We don't actually need the value. we'd get, what would we get? We'd get the A, and then we'd go F. Oh, no, we wouldn't. We'd just ignore the result, and then we just go, yeah, that probably. So the problem with this is that we've taken the envar and it says, okay, nothing. Like there's nothing there. And then we're like, okay, well, oh gosh, let's put something there. But what if between these two times, someone else, like another thread, puts to the envar? So we've, the state of the world as we see it is like there's nothing in the envar, but in between these two lines, someone can put something in the envar. And then we're kind of doing the wrong thing, like where someone else has already refilled the value, and then we're refilling it, which might not be an issue, but well, actually, in this case, it's going to be an issue because put envar, I think, blocks if the envar is full. Um, yes, it'll wait until it becomes empty. So this thread will block. We could use write envar instead, which I think is just like write through. Um, but still, that's not ideal. So that's an issue. Like, the problem is that kind of there's a difference. Like, this is not an atomic transaction. Viewing the state and then putting in it. So what we can do is if we use the TM bar from the STM package, we can put this in atomic transaction. So like nothing can happen in between these two. The state of the world remains like the same or consistent. So we can instead, we have to work a little bit differently, but I think it'll be good. So we take the envar in case it's nothing, then, okay, so in case there's nothing in the envar, then we're good. In case there is something in the envar, in case there is a B, we should take that. Maybe I can't work around that. Hmm, let's just try it. What's going on here? Okay. Oh, okay. So this will ensure that the envar is empty. Because we want to make an update to it. The issue with STM is you can't do IO inside of the STM. It's not an issue, it's like a decision. You can't do STM inside, you can't do IO inside the STM block. So we just have to be careful about how we do this so that it stays thread safe. Because, at this point we know it's empty, but as soon as we get out of that block, it could change. Well, no, actually, if we're the only one manipulating this envar, so only this module, which is fine, we just won't export the constructor. We know that the tmvar is empty now, and no one else can take it because, okay, that's what we've got to do. We're just going to take it. So, uh, so we could just take the envar. We just take the envar, and then if the envar is empty, we just wait, which would work for us. But if we're the only ones using this module, which is fine, we can do that. The problem is that initial point. It's like when we initially defer this computation, there's going to be no value there, and so we need to think about what happens then. So we need some way of marking, like, okay, this is the initial computation. Like, um, we can't take the envar because it's going to be empty. So I think how I worked around this before was just I made this a maybe and just never let the envar be empty. UT envar IO nothing. And then when we go to eval it, we just take the envar. And in case the bar is like nothing, just take it. Sorry, this is my foggy brain this morning. So in case the value is nothing, then we create and we stm atomically put tm. But if it's just B, see what I initially did. This is a little bit easier for me before because initially I would just like return, um, if the value was already full, I would just return that value. Because I was like, oh, why would I want to reevaluate the computation? But the problem is that there are resources that need to be recreated more than once, like the render pass or a swap chain or that kind of thing. So my previous design doesn't work, which is why I'm having to think properly today, which is not working out super well for me. Um, yeah, but we're doing something different now. So if the value is already full, then what are we going to do? Well, I think this computation should take the previous value if it's there, because uh, we might be able to reuse some of the resources. So we'll pass that in. And in the case that it's full, again, we do the same thing. Okay, you can see that these two cases are exactly the same. So we can just get rid of that. Okay. After all that time. So what are we doing? We're taking the TM bar and okay, what if we get an exception here? We take the TM bar, we uh, use it to, what do we do? We use it to create a new one and then we put it back. The issue we have at the moment is if there's a asynchronous exception, we're in trouble. So we always want to put something back to the TM bar. Restore exceptions for the duration of computation that the user has, and if there is an issue there, then we put back just the old value. And we'll have to we'll need a can't you just automatically import for me? Alright, so we're taking the TM bar, running the user's computation. If it fails, then we're putting back the old value, and otherwise we put back the old value. Put back a new value, sorry. So do we actually need this to be maybe? We do. So the only time it should be nothing is initially. Because we can't create a computation that writes back a nothing. So we'll just work with that. We'll go with the flow. We'll see what happens. I think that's fine. Okay, so I expect that the user will be deferring the computations. I expect that us on the renderer side will be evaluating the computations. So what is something else that we might need to do? So we might need to get this initial value. So we might need to get the seed that's used to create the final value. What am I doing? Can't spell. And what we're going to do here is I don't know if we should just try and take the the var. Yeah, okay. So we just try and take the var, well, we do take the var, because it's always going to have a value, either nothing or just. In case b of nothing, we're going to throw an exception. It's like, uh, otherwise we'll just return a value. And ta-da! So the user will be passing around the handle, which is this deferred value. And at some point, like in the draw loop, we might actually need to get the render pass. So we use this unsafe get. The reason it's unsafe is because the value might not be initialized yet, but it'll be safe for us because we'll essentially in the render module, we'll kind of make this guarantee that by the time we get to that draw loop, the values will have been evaluated. And a safe get would look something like um, let's just get rid of that. What would a safe get look like? We'd take the TM var. Oh no, we can't take this. We need to read it. Because if we take it, then it's not there anymore for anyone else. So we read the TM var. So if it's nothing, well, if it's just, that's the easy case. Pure B. And if it's nothing, then we kind of need a computation to run to populate it. So yeah, we'd probably just need to eval. So it looks something like this. So it looks exactly the same as eval, except this one would optionally evaluate. So we'll call it okay. I think that's what we need. So I think it's fine, but it might be a little bit janky, but it's okay. We can come back to it. The interface will be pretty similar. Unsafe get and get seed. Cool. Oh, hello. Okay. All right. So the more interesting part is how we're going to use these. So let's have a look at that. let's go to our render types. Because we're still going to be using some of these, but we're going to let's start with a shader. So the information required to create a shader. Do we have any of that here already? No. Right. And we're going to have an interesting use of acquire for the first time, which I hope you'll enjoy. So what do we need to make a shader? The user needs to tell us. We're going to give the info like suffix to anything that essentially is going to be used to create the final product, and we'll just use the we'll use no suffix for the final product. Um, so you need to just tell us the shader stages, or the shader stage usually, that the shader is a part of. Is it like a vertex shader? Is it fragment shader? Go tell me what the entrance function is. Usually it's just main, but we'll make it flexible, and then data. So yeah. So we've got a strict byte string for the entry function name and a lazy byte string for the data. So I'm going to go with lazy byte string so that we can maybe stream from the disk if possible, instead of loading everything into memory at once. But whether or not we actually make use of that, we'll see. So we'll have to import, see if we can automatically do it. Yep, and import byte string lazy, and we'll have to import acquire. So here's the interesting thing. The user's giving us an acquire, so they're not actually giving us the data to the shader. Like they're not giving us a byte string. They're giving us a way to acquire the byte string. So that means that we can defer when we acquire that byte string to like much later on, because it's not like the user's giving us all this data and then we're just keeping it around in memory. They're giving us a way to get that data later, and we don't need to keep it around in memory. So like we can get it when we need it. And then that's like a simpler way of managing lifetimes. Like it's if the user has to acquire the resource and then give it to us, they're also the ones who free the resource. And so they've got to make sure not to free the resource until after we've like used the data to create the shader. And that's a problem if they don't know when that's being created. Like if we've deferred it till like a later point in time and they don't know when they can free the data, that's like a real problem. And is annoying for everyone. It's annoying for the library author because they have to make a way of signaling that or document that. And it's annoying for the user because they can't just get rid of their data when they're done with it. And all that a shader is really is just this pipeline shader stage. At least that's all we care about for now. Create info structure. So you can see these. Let's have a look. Pipeline shader stage. Here we go. So what we're going to do is we're going to read the file, the data that the user gives us. Oh, excuse me, one sec. Oh, yep. So what we're going to do is we're going to read the data, allocate a shader module, and then create this pipeline shader stage. And the shader module's in that. Okay. So now we can introduce our handle type. This is what the user's going to use. So we've got a way of creating a shader handle, and that's going to be a deferred computation that takes the shader info and then produces a shader. So I hope that kind of makes that deferred computation thing a little bit clearer. If you have any questions, yeah, please let me know. Essentially creating a way to go from the shader info to the shader, but we're deferring that computation until later. And we're just giving back the user a handle to the shader. So from their perspective, the shader's been created, they can use it, there's no problem. Okay, cool. So how does the user actually create a shader though? So we'll go to render. Oh, what's going on here? No. Render.hs. And we'll style this up here and well, what should we call it? I think we just call it shader. Let me just do a little bit of thinking. Uh, yeah, let's just call it shader. So it's going to take the shader stage, the byte string for the entry function, and then a way to acquire the data for the shader. And then we'll give them back a handle to the shader. Add the imports. Blah, blah, blah. And so we're going to create a shader handle by deferring the shader info. Shader handle. And it's going to need to be monad IO because that's what the defer function is. Great, there we go. So what if we just have a look on this right hand side here? Also, please let me know if this is too small. It's something I always don't think about. Yeah, if we're on the right here, we've got our main function. The user will just be like, okay, shader, vk, vertex, uh, shader bit. What is that? Shader stage vertex bit? Yep. So I'll be like, there's my vertex shader. Main is the entry function. And then we're going to need to create an acquire. So make acquire. And it'll be like, we can actually just, it'd be like open file vert.shader and then close file. And that would be it. But what we can also do is because acquire is an instance of monad or applicative and this shader is like pretty small and we're using lazy byte strings anyway, can probably just do like, just go pure file and then vert.shader and that should be fine. Let's just put it here. Sorry, not pure, lift.io. Yeah, and so that would work. It return them like a shader handle. They might be like vert shader, and then they can like use that. So what they'd probably use that for is like they'd use that in a subpass. So they might be like subpass one, and then be like subpass, then some like subpass info, with like shader equals, right? And then later on in like the draw calls, they'd submit a draw call that's like, submit draw subpass one, and then like draw mesh or something. Just making it up, but yeah. So that's how it works. So we've done shaders. We should probably have some way of loading the shader. Let's actually run that computation. So load shader. Let's call it eval shader. To match our yeah, whatever. So we're gonna need our VK context, shader handle, and like you notice that like we haven't even introduced like a renderer or anything here. Um, like this handle is essentially like a handle into like the Haskell runtime system, and like it's maintaining that, and then we can use that as well. So like we don't need to have like a renderer data type that's holding all the handles, or any like pool data type, like in this high pipe example, that's holding. Oh, where is that? Which of these main tabs? Yeah, like they've got a pool which is holding all the data. Like we don't really need to do that. We can just do this. And if we want to keep track of any handles, we can. We will later. But if we don't need to keep track of the handles, then it's fine. And I imagine what's going to happen is that, um, the first time we get our first set of draw calls, we'll have a look at what render passes we need, what shaders we need, and we'll go ahead and like eval all of those. Um, and the user will be passing those handles to us via the draw calls. Um, and then for efficiency later, maybe we do keep track of all of the shaders and we load them all at once before that first frame. Um, but that's kind of up to us. So this is going to return a shader. So context and then the shader handle. We've got our deferred computation in there. And let's open up our deferred module. Eval to deferred computation. Oh, what should we do? Just wondering if we use the eval empty function or the eval function. Because the eval empty is going to replace whatever's there. Whereas eval empty will only place it if it's empty. This is interesting because it might not be like. Yeah, let's just eval empty. Like, let's just only do it if it's empty. For us to eval shader and there's already a value there, I don't see any reason why you'd want to recreate a shader like that. Because there's no way to change the initial value, so you just have to, if you want to change a shader, you'd have to create a new shader. The only instance I can think of where you'd want to reevaluate if there's already a value there is with the render pass, because like I said, whenever the swap chain changes, we need to recreate the render pass. But for now, I think we can just expect that the shader is going to be empty because, and if it's not empty, then we just return whatever's already there. So what do we got? We got our create info, that's there, and then we've got like a maybe existing value. This should just be B because the value should, wait, hang on a sec. So eval empty, like the value is this maybe B, is like always going to be nothing. So we shouldn't really need to worry about that. So what are we going to do? We're going to create a new function, a existing. So we're just going to ignore whatever's the existing IFA. There we go. So all we did is just make that A to MB match that A to maybe B to MB by ignoring that second parameter. And that way here, all we need to do is like we've got the create info. So instead of having also here like a maybe existing value, which like I said, we don't expect that to happen. And if there is an existing value there, we're just going to do nothing. So, okay, let's create this shader. So, first we'll create the shader module. So with the create info data, so we'll get that byte string with the shader code in it. And we'll just use with, because this is, remember this is an acquire type, and we'll just use with to acquire it for the duration of this block. Then we'll create the shader module. So it's got like the release key and then the shader. So with vk shader module, vk device, context, and vk.shader module, create info, k.0, to strict shader code. So shader module create info requires that the shader code that we pass in is in strict form. And then once we've got that, we can just return the shader. Just put this here. vk.pipeline shader stage. Because remember the final form is just this shader stage create info. Blah blah blah. And create info.shader stage. And shader module. And create info.entry function. And nothing. So I'm using overloaded record dot here. If you haven't seen that before, it just lets you like dot into things like in other languages. Now, have I done everything correctly here? So do we want the release key? Do we want a way to release the shader? Probably not. It'll get released anyway because we've allocated acquired it. But right now we don't need the release key. Maybe at some point in the future, but no. Okay, got some issues, so let's see what they are. Oh yeah, we should just return that. What have I done there? Need to import a few things. And make sure that we're using overloaded record dot. And let's see what our other issues are. Import exceptions, import with. Oh, we need unleft IO as well. Okay, looks like we finally got here. And need to import GATTs as well. Okay. Great, no warnings. Alright, that was a bit of a long one, but now we can load a shader. So we've got a way for the user to declare a shader that will be created at some point in the future, and then we've got a way to actually create that shader. And we've also got a way of getting the final value. Okay, let's move on. So today we'll just give this kind of handle treatment to all of our resources. So we'll be looking at vertex buffers, index buffers, and like subpasses slash render passes. And I'll also have a look, kind of show you some of the other research I was doing into kind of the flow of how these resources are created. So, like for example, when there's a swap chain out of date event, we need to recreate the swap chain, which means that we need to recreate swap chain images, which means that we need to create the recreate the render pass, recreate the frame buffer, blah blah, and also recreate the pipeline layout. And we kind of just everything that's little like downstream of this swap chain will need to be recreated, except this. And yeah, so I'll go through that later at some point. But for now, I'll just take a little break and then we'll come back and we'll have a look at buffers and loading data from buffers because it's just a little bit more interesting with the kind of deferred acquire sort of thing. So we'll have a look at that next. Anyway, thanks for being here and I'll see you in 10 minutes or so. Okay, we're back. All right, so the next thing on our list was the vertex buffers, or the buffers. Ah, let's have a look. Um, blah blah blah. Sorry, just okay. So types. We're gonna have to make a new handle type. We'll call it buffer handle, and it's gonna create. It's gonna take some buffer info, return a buffer, and then so do we already have buffer info? No, I misspelled deferred. Very easy to misspell. Is that how you? Yeah. Okay. All right. So buffer info. What do we need to create a buffer? Well, the first, I think we need the data. What else? The usage. That's it. So usage, buffer, buffer usage flag bits. So that's like, is it a uniform buffer? Is it index buffer? Is it vertex buffer? And the data acquire. Gonna need the size of the data, and then like a byte string. And yep, we're gonna use duplicate record fields. That should be enough. And the buffer itself, it'll just be probably just a buffer and an offset. So yeah, it'll just be the Vulkan buffer. Oh, okay. And then an offset. Okay, cool. And now we'll give the user a way to create a buffer. Buffer. It's going to be monad.io. Buffer usage. We should document. So this might be like a vertex. And the other thing we need is a way to acquire the data. So this first parameter is the size of the data. The reason we need that is otherwise we have to stream in the entire byte string just to figure out how big it is. And that might not be what we want. Um, like, let's say we have 4 of these and we want to, or 100 of them, and we want to allocate a buffer big enough for all of them. We can't read every single one into memory because that's what if each file is 5 MB big and then we load in 100 or 1,000 of them. That's going to be a lot of memory. then it's gonna be slow. So it's better if we can just get the size straight away. And like that's easier for the user. What they can do is they can, you know, write the size of the buffer. Like if they've saved a OBJ file, they can write the size of it to the, I don't know, to a metadata parameter or to a like header in the binary file. Um, yeah, and then that way we can just get the first block of the byte string and the uh, size of those thousands of buffers, and we won't have as big a problem with memory. I hope that makes sense. I didn't explain that super well, but we'll see. Okay. So we've got a way for the user to create a buffer handle, and then we should create a way for them to evaluate the buffer. This is going to need all the same stuff that this other one had. So monad unlift IO, monad mask, and monad resource. Mm-hmm. So you've got our create info, and then with the data in the create info, we will get size and then the bytes, so the binary data. Then what we'll do is allocate, we'll allocate a we'll use the allocator to allocate a buffer for us of the appropriate size and usage. Then we'll get a pointer to the allocation. And we'll put some data there. Some things. And then we'll flush the allocation and get the allocation buffer and offset. Okay. Yep. So the thing that we're missing is that we don't actually have I don't think we have a way. Don't remember, did I do that? Yeah, we don't have a way of allocating a buffer using the allocator. I mean, we kind of do in this uniform buffer thing. This is allocating a buffer, but this is a specific type of buffer where we're actually wanting to create like a GPU buffer. Whereas with the vertex buffers, we don't mind if it's initially on the GPU or on host. Um, it's either like we'll just ask it to kind of allocate a like a GPU buffer, GPU backed buffer, and if not, it'll give us a staging buffer, and then like we can transfer the data from the staging to the GPU backed buffer. Um, yep. So we'll need to actually create those functions. So let's go ahead and do that. Da, da. So we'll start off with some data types. Oh, data. So the type of what we get back from the Vulkan memory allocator is this. It's like when we ask it to create a buffer, we get back the buffer, some allocation info, and the allocation itself. And there's two types, like if we ask it for a host visible, which means that we can write to it, and GPU, so device memory backed buffer. So essentially like give us a GPU buffer that we can write to. If we ask it to do that, it has two options. Like it can either do that or it can say like, no, I'll create that buffer for you, but you can't write to it directly. You've got to like go through a staging buffer. Um, so from our point of view, we've got two things. We've got a device allocation or we've got a staging allocation. We've got a staging allocation, we've got two, and the device allocation. So when we ask for a buffer, so given an allocator, the buffer usage, the size, give you back an allocation. So I'm just going to copy this from the uniform buffer example. So we've got some allocation create info. So we're kind of letting the device or VMA, like Vulkan Memory Allocator, decide the usage, but we're saying we want to be able to access it. We say like, but if we can't, then it's okay. We can just use a staging buffer and transfer instead. And we want to like create it mapped so that we can like write to the pointer immediately. Um, the buffer create info. Yeah, we're just using the usage. We've got a sharing mode. Can come back to that later. For now, we can just call it exclusive. And there, yeah, from there, we can make an acquire that tells it how to create the buffer and like how to destroy it. And then we get the memory property flags. So we now need to check like what type did we get. So if the memory that we got is host visible, then we know we've got a device allocation because we made one allocation and we can actually write to it. So we've got device allocation. But otherwise, what we need to do is make another allocation for the staging buffer. So I'm just going to copy this in because I've already written this and it's quite boring. So let's not do it again. Okay. So in this case, the usage, uh, it doesn't need to, like, the usage that they will specify will probably be like vertex buffer or index buffer. Um, the staging buffer, it doesn't need to be have that usage because we're just going to use it as the source for a transfer operation. So that's the only usage it has. And then we ask again, you know, please make it so that we can access it and create it mapped. And so then we, yep, do the same thing. Go ahead and tell it how to make that allocation and how to free it. So we're in the acquire monad, remember? And then we go, okay, staging allocation. So this is the second type. We can just call this staging. What's happening here? Ah, okay. Apparently we've got some bad indentation. Okay, I think that's good. So this bad indentation. Da da da, that's two in, that's two in. That's two in. What's wrong with you? Oh, there we go, missing a bracket. Missing some imports. Okay. And yes, missing a few functions. So we've got a way to allocate a buffer, but we need some way of writing to that allocation. So this is device allocation. We're just going to write directly to it. So we can ignore the buffer, we can ignore the allocation, but the allocation info we'll need. Oh, we don't even need the allocator. Staging allocation. Here we write to the staging buffer and ignore the device buffer. But yes, if we've written to the staging buffer, let's give this a type signature. Yep, so if we've written to the device allocation, then the data's there. We're all good. But if we've written to the staging allocation, we now need to copy it to the device buffer. So, yeah, I'm not sure how we're going to do that yet. Like every time someone allocates to the pointer, we could put a TQ in the allocator and like say like this is gonna, we're gonna need to flush this at some point. But right now I'm just gonna like create a flush function and what we'll do is we'll actually just leave it as empty, so it'll do nothing essentially. Um, yeah, because like I'm just not 100% sure like how we're gonna do this yet. Because copying a staging allocation, we need to issue like a copy command, and then we need to set up like pipeline memory barriers to essentially say like don't start rendering vertices until you've flushed this data. Um, and I'm just not sure how we're going to do that yet. Like the renderer that we're building hasn't really like materialized yet. And I think we should wait until that point before we decide how we're going to flush this stuff. But we'll provide the operation so that like we're thinking about it. Um, and this kind of code makes sense. Um, yeah, but yeah, we just got to remember that this code won't actually work until we go ahead and fix that. So we've left a little to do there. We'll come back to it because we don't want to do too much work um, until we're sure that the work is going to be useful. And let's just create two little functions for this. So the allocation offset is always going to be 0 because it's just the way Vulkan memory allocator works at the moment. So yeah, just leave that. And what's to do? Actually, let's just make this undefined so that yeah, it'll throw an error. Buffer. Great. Um, okay. So we've got a way to for the user to create a buffer. We've got a way to evaluate the buffer. That kind of doesn't work, but you know, the idea is there, the thought that counts. Um, so we should move on to subpasses and render passes. So for now, let's commit this allocation work. Well, let's start with defer actually. So defer. And then uh, work in progress implementation of allocation of buffer allocations. And then we've got uh, handles. Yeah, so I forgot to say, so all of these videos are uploaded uh, after the stream to YouTube at SamBNT_TV. So I've got a playlist. You can go ahead and see all of the previous videos. Um, and you can follow the code at github.com/RORT. Sorry, github.com/SamBNT/RORT. So you can see the commits that we just made there. Great. You missed anything? Okay. So we have a look at a triangle example. Uh, we'll start again with a triangle example. So we've got the shaders. We've handled that. There are no buffers in this one, so that's nice because like that way we can kind of skip this whole buffer allocation not actually working problem until later. So we'll try and reproduce the triangle example. Um, but the thing that we're missing is like, yes, we have the shader, but we don't have any way of using it because we haven't got this concept of a subpass yet. So what we're missing is the subpass and probably just a draw call. Cool. Subpass and draw call. All right. So yeah, subpasses are a little bit interesting. So at the moment, we've got a render pass and it's got like a list of subpasses because that's how it works. Like a render pass is like, this is the layout. You're telling it like the layout of the render pass. You're telling it what image attachments to use, um, what clear values to use. And then subpasses, like they're essentially just like subpasses are like any render pass that shares the same layout. So it's almost like you can think of the subpass as the render pass. That's the thing that's doing the rendering. But then the render pass is like the layout for all of those render passes that share the same layout. Um, so yeah, I'm thinking of renaming this to render pass layout. Get rid of the subpasses and have each subpass have a render pass subpass, or maybe just a subpass layout. That's like render pass layout. Yeah, thinking that, but what would that actually look like? Um, so at the moment, the only way, like in the future, we'll have more render pass information that we'll need to work with. But for now, we actually don't need any information. Um, there won't be the draw anymore. The shader stages, this is going to be a list of handles to a shader. We can ignore the descriptors and all that kind of stuff for now, but that's all good information. We'll need that. And we'll just add another type here, subpass info layout. And it's going to be a handle to a render pass layout. So once you create a render pass layout, you can start creating subpasses within that. You can get rid of that there, get rid of that. So subpass is just the pipeline layout. We can get the render pass layout from this. This doesn't need to be a list. From the subpass info. Let's put these in a bit of order. The render pass layout is just going to be the Vulkan render pass. We can get rid of this, and actually, it's going to have a list of frame buffers as well. Give me a sec. Let me just refer to my notes. Yeah. So each render pass, it's going to have a list of frame buffers, one frame buffer for each swap chain image view. So frame buffer is like a collection of the actual image views. So the layout will be like, I'm going to use one image layout, and that's going to be the swap chain image. Or maybe I'm going to use two. One's going to be a swap chain image, and one's going to be like a depth image, like a depth buffer. And then what's going to happen is for each swap chain image, like we might have three swap chain images, we're going to create a frame buffer for that render pass. So that's kind of if we have a look at this structure, this thing here, um, for each swap chain image, for each render pass, we're going to create a frame buffer. And then when we draw, like whatever swap chain image that we're rendering to, we'll grab the index of that. We'll grab that frame buffer by indexing into this array. So I hope that makes sense. Let's start with the render part. What are we going to call it? A render pass layout handle? Deferred render pass layout info. And I'm going to produce a render pass layout. And the handle type is going to be render pass layout. Cool. Let's put this on a new line so we can read it. Excuse me. Dial 2. Okay. Let's go and make a render pass layout. So yeah, we're going to create a way for the user to create one of these. They don't actually have to give us any information at the moment because we're hard coding a lot about the render pass. So for right now, because like typically they'd have to say like what kind of images they want to use, like do they want a depth buffer or do they want like 4 images that they're going to render to? But at the moment we're just hard coding it to like one image, which is the swap chain image view. So this is actually a little bit easy for us. Sorry, render pass layout handle. And we're going to defer and just create render pass layout info. Great. So that's how they create a render pass layout. And let's evaluate the render pass. This is going to be interesting. I'm not sure what this is going to be like. Context, render pass layout. I'm going to create render pass layout. Okay. Now I've got to go back to my notes for this because I don't remember how I did the render pass bit. Let's have a look. Okay, looks like the thing I did is that we're going to create a renderer to hold the current swap chain. And we're going to read that swap chain value. We're going to then allocate a render pass using the swap chain data and also allocate the frame buffers. Okay, that makes sense. So yeah, something I kind of run into is like, there are all these like data dependencies between like the swap chain and the render pass, like, and then from the render pass to the frame buffer, and from the frame buffer to the draw call, and there's just these data dependencies where like if we update the swap chain, we also need to update the render pass, kind of like and basically immediately. So like one way we can do that is like we can wait for this swap chain out of date event and then do all of this work after the swap chain out of date event. Um, but I don't really feel like that models the problem very well because like really it's about the relationships between these things. I'm sorry, this is so like white. Let's see if I can make that better. Let's make this dark gray center back. And I really wish Figma would add like a white. Sorry, dark mode. Alright, this will be a little bit better. Let's make it even better. Can we make it like black? Or a custom color maybe? And dark gray. Okay, cool. So yeah, like quite a lot needs to change actually when the swap chain changes. The images, which like we kind of handle automatically, but yeah. The images, the render pass, which then changes the frame buffer, but the render pass also changes the pipeline layout of any subpasses, and because subpasses are specialized to a particular render pass, and the graphics pipeline also needs to change. I mean, things like the shader module don't need to change. Um, but yeah, there's this like dependencies. Uh, and yeah, I just didn't really feel like that waiting for this event and then just updating all of this. It's not bad and it's not incorrect, but I would prefer to model this as like, okay, the render pass, it depends on the swap chain. So whenever the swap chain updates, please call a handler that also updates the render pass. And then, that also calls the handler that updates the frame buffer and calls the pipeline layout and the graphics pipeline. So we specify our code as like a series of dependencies, and then we have like some external runner that just and runs that and updates everything when it needs to update. If we update just the render pass, then we need to update these three things, but nothing else. So I had a look at that. Like I was looking at particular like functional reactive programming. Um, in this case, I was looking at deny, um, and also at reactive values, which are mentioned in this paper. Uh, on and on. Here we go. So there's the idea of like these reactive values where, let's see if we can find an example. Yep, so they got this example where, whenever you update text field 1, text field 2 updates. And then like whenever you update text field 2, text field 1 updates. So they're kept in sync. They're like, I don't know, you can imagine two text fields, and they just always have the same value, but you can edit either one of them. Um, so yeah, I've thought about modeling um, our program here, or like this part of the renderer, as these sort of reactive values, so that if I update the swap chain, a handler is called that updates the swap chain images, and is also called to update the render pass. And then the render pass, you know, the handler is it's updated, so the handler is called, and then that updates the frame buffer. So, just naturally everything updates. Um, and that's useful because if we add a new subpass, then we're going to need to create a new pipeline layout and like set up handlers for all of that. Um, yeah, but the simple way of doing it is like we just keep a list of render passes, and we keep a list of the subpasses, and then whenever the swap chain is updated, we just go ahead and read that list and just update each of the handles, and same with the subpasses, read that list, update each of the handles, and then we're good to go. So I'm not sure which way I'm going to go because the reactive values way is promising and also like leads to kind of better, it looks like better code. easier to read, the relationships are clearer, and they're explicit. But the easy way to go is just, yeah, keep like lists of the render passes and subpasses around and just update them whenever that event occurs. Then the dependency is implicit, which means that it's not so easy to understand. Like the code doesn't explicitly say like this depends on this and this depends on this, which kind of sucks. But yeah, yeah. So I think for now, like for today, we'll create a renderer type and we'll store the swap chain in there and we'll just store like anything that depends on the swap chain in there and we'll just do the dumb way because like the smart way might take too long. So, and I'm honestly not even sure how that would work. Like, uh, there are two sources of events. There's a window resize, then we know that the swap chain's out of date, and there's a draw call. Um, like when we make a draw call, like when we're presenting, it'll say like, oh, the swap chain's out of date. So those are the two ways that we know the swap chain's out of date. Those are the two producers of swap chain out of date events, and those events should push the swap chain to be recreated, which will then push for the images to be recreated, which will then push the render pass and then push the frame buffer, push the subpasses. Um, yeah, so that would be ideal. But for now, we'll do the dumb way because I'm not actually sure how to implement the other way. I was trying, like I was desperately trying to do this before um, before we got to Thursday and we have a new stream. Like I'm trying to get this to work, but no such luck. So what we'll do is we'll keep the swap chain in a mutable variable uh, so that we can share it between threads. Um, what else will we do? We'll keep the frames in flight here. That way the renderer knows how many frames that it can render to at once. And we'll keep the passes here. So a TQ handle render pass layout. And at some point we'll also keep the subpasses. Let's call it layouts and passes. But we're just going to comment that out for now because we don't actually have any handle to subpasses yet. Cool. Now, a lot of render operations are going to need the device. I just know that from the research, so I'm just going to put that in. Okay, we're going to need some way of creating the renderer. Need the context. So we'll start with swap chain. Already got things for creating the swap chain. We'll create a swap chain var to put the swap chain in. And then we'll create a new queue for the passes, for the layouts. New TQ IO. And what's the final thing? We need to create the frames in flight. And finally, we can return our renderer. So renderer, got the swap chain var, frames in flight, the layouts queue, and we'll grab the device from the context. Cool. My indentation's off here. Off by 1. Okay, so I've changed some of the types here. So make frame data is going to be not working, and same with record frame data. So get rid of those. Oh, okay. Get my Haskell language server working again. And we'll go ahead and import what we need. Some more importing. And then we're gonna get rid of these examples because they don't work anymore. We've changed the underlying render types. So yeah, they're not going to work anymore, but that's okay. We'll fix them later. Just want to make sure that we can still compile. Okay. Let's go ahead and start evaluating this. So when we create the render pass layout, we're actually going to ask the renderer, because we're going to do two things. We're going to create the handle, then we're going to write the handle to TQ. So renderer layouts, I'm going to lift IO, STM atomically, STM, we're going to write TQ. So write to that queue the handle. And we've got to import this stuff. And return the handle. So that way we keep track of all of the render pass layouts that we have, so we know which ones to recreate. And to make the interface consistent, when we create the shaders and the buffers, we're going to ask also for the renderer, even though we ignore it. Because that'll create a consistent interface, and we'll probably want to keep track of the buffers and shaders and stuff at some later point in time anyway. Okay. So, eval render pass layout. So this is going to be an example where we don't use eval empty. We have a look again at our util defer. So eval only evals if empty, but what we're going to do with the render pass is always evaluate, because we've always got to check if the swap chain's changed, or do we? We don't actually. We'll only eval if empty, and then if we get a swap chain update exception and we're handling that at some point in the handler, we'll get all of the things out of the queue and then force the eval then. But for now, just this part here, we'll just eval empty. So, just gonna open my notes again. This is like the render pass info, which we don't actually use. And I think what I'm going to do, because this thing's going to be recreated, it's good to have not just the render pass layout, but also the release key, so that we can release the resource when we go ahead and recreate it next time. Yeah, we're going to release the old resource, create a new one. So our handle type will stay the same, but it's also going to give us some extra information, which means that when we eval, we need to also create a release key. That's exactly what allocate acquire is going to do. It's going to create the render pass layout and also give us the release key. So here we go. Here's our very hard-coded render pass. Let's get rid of this argument until we actually need it. Okay. I'm going to copy this from our existing create frame data function, because nothing's changed. We're just creating like basically a hard-coded render pass with one attachment, which is the swap chain attachment. We actually need the swap chain, so we're going to have to read that variable. And then afterwards, we're going to get the frame buffers for that render pass, like this. And then we'll return the render pass. It's render pass layout, I think. Render pass layout, yes. Okay. Do some imports. Some more imports. Okay, we're going to need to read the swap chain from the renderer. So, where is that? Where is that? Okay, we're going to need to pass the renderer in. Because we only use the device from the context, let's make this, let's pass in the device to the renderer, like we were. So yeah, we're just reading the swap chain number. And using that to create the render pass like extent. Import this. Now it looks like the only issue is the type of this. So the issue is that what is the issue? Did I not save this? Oh, this is going to return the release key and the render pass layout. And we need to just return the layout. Gosh, that was a lot. Okay, so we've got a way of creating the render pass layout. Let's change. Yep, any usage of the VK context. Oh no, we need that there. We'll just keep that like that for now. A little bit inconsistent, but that's okay. So yeah, the user has a way of declaring the render pass layout. We have a way of evaluating the render pass layout. Okay, we should move on to subpasses. Then we'll have enough to declare our triangle example. It'll just be two shaders, a render pass layout, and then subpasses. That's enough to render the triangle. But then the next thing we'll have to do is kind of take the user's draw calls and actually present an image like from their draw calls. So yeah, But for now, I'll take a little break and we'll be back in 10 minutes or so. So thanks for watching and see you soon. Okay, we're back. Right, so done the render pass layout, and now we should look at subpasses. So a subpass is made up of a handle to the render pass layout, handle some shaders, then just some other information that we won't be too concerned about right now. So what we've got shader, buffer, render pass layout. Let's add a subpass. Yeah, if anyone has any ideas on how to model data dependencies well in Haskell, such that like we can like express the relationship between data dependencies, and then when some part of that relationship is updated, all the rest downstream updated, that'd be great. Because I'm a little bit stumped there. We need. Let's just take the subpass info structure. And we need a subpass handle. Cool. Okay. We're going to write the handle to a new queue. It's called the renderer passes. Make sure to create that new queue. Call it passes queue. Okay. There we go. So we got a way to create a subpass. Now we need a way to evaluate subpass. Got our deferred computation in this handle. We'll eval if it's empty. Um, Now, to create a subpass. So we need some way of getting the render pass. So we've got the handle to the render pass. Render pass handle. Got the deferred computation for the render pass. And that's just subpass info layout. Subpass info. Let's give this kind of record dot syntax treatment. Okay, so we can get the layout That gives us the deferred computation. Now we actually need the render pass. So what do we have? What tools do we have for getting that? We can use an unsafe get. But we'll just call eval render pass layout. And if the render pass is empty, then it'll um, it'll create one. But if it's not empty, it'll just return to us what is there. So eval render pass layout, we'll need to give it the renderer, the handle, and then we should get the render pass layout. And the render pass layout is made up of, let's just go ahead and probably won't need the frame buffers. Cool. Now we can create pipeline layout, which doesn't depend on the render pass actually. So maybe we should just do that first. Do this later. Oh, no, it's fine. So pipeline layout, just copying that from before. We'll also need to get the shader stages. So again, that's going to be so shader and what's in a shader? Got the stages. We got the stage. So we're going to eval all of the shader stages that we have. So eval shader, renderer, we're going to map that over the shaders in the subpass. So subpass info dot shader stages, I think. Let's have a look. Yep. So it's going to give us a list of handles. We're going to map over those handles and eval each shader. That's going to give us back, where's our shader? It's going to give us back a shader. And let's make this renderer and renderer device. Cool. So that'll give us back a shader. And then out of that shader, we're going to get the pipeline stages. So we can just put that in here actually. Can I just do this? Maybe, we'll see. Call this pipeline shader stages. I think that works. 96. Oh, looks like we've got some pass error up here. It's kind of weird. I'm confused. Oh, it's over here. Oops. Okay, we'll import. No. Yes. Import everything we need. Okay. Great. So we got the pipeline shader stages. All right, now we can create the pipeline. And I'm again just going to copy this from our create frame data function because we've already done all this work. Um, Control C. Okay, so got to indent this properly. So we're just creating the graphics pipeline create info structure. Attributes. Let's go through and fix anything up. Oh, we don't have the subpass index. That's interesting. I think. Okay, we're missing a few ports. Sorry, my Haskell language server is being slow. Yes, and then it's going to give us back a release key and the subpass, and we're just going to return the subpass. Okay, what else have we got? This is not in scope. And then we should just have the subpass info index problem. Okay, so one of the nice things about specifying the render path layout and then all of the subpasses was that the index was implicit because you just have a list of subpasses and you could just say the index was whatever the index of that particular subpass was in the list. But if we create the subpasses separately and point them towards the render path layout, we're going to need to specify the index as well. This is not my favorite. Maybe we can think of a better way of doing this. But for now, we'll just do it like this. Okay, some struct. Hmm. Interesting. So eval render pass layout requires, well, actually, it's just uh, requires unlift IO. That's a problem here because acquire isn't an instance of unlift IO. So see if we can get rid of that requirement. What does require that? Looks like I can get rid of the unlift IO example, but then I still constraint, sorry. But then I still have an issue where I need monad mask. Yeah, that's not going to work. All right, let's pull these out. Oh, I can't even pull it out. Um, hmm. Let's have a think. Hmm. Oh, yeah, this is kind of a problem. This is where the data dependency stuff might be helpful. The issue is like, this is mainly just a constraint issue where a value render pass and a val shader require a few constraints that acquire the monad that we're operating in can't satisfy. Um, but also I'm just realizing that, this render pass layout could change in the time that we actually create the pipelines. But maybe that's not a big deal. Oh, so what we'll do is get the render pass layout and the shaders first. Then just indent all of this. What's going on here? Oh, okay. See, she's just up here. Shader, pipeline shader stage. Eval shader should return. Ah, let's just get the shaders first. Great. Okay, got that working. Still prefer the data dependency way, but oh well. So got a way of doing the subpasses, render passes, shaders, and the buffers, but that doesn't quite work. Um, so we should have enough to kind of declare our triangle example. So if we open up our triangle example, it'll look something like, get rid of all that and just be shader. Oh, first thing, we'll create a renderer, context, uh, num frames in flight. That's going to give us a renderer. Then we can feed that renderer to the shader, be like vk shader stage vertex bit, and entry functions main, and the data is lift.io read file, and we've got that file up here. There we go, vert shader. And they've got the frag shader. Try.frag. And then don't need any of that. So we got shader, and then we just need the render pass layout. So layouts, render pass layout, pass in the renderer. But that's all we need to do. Subpass 1, subpass renderer. Now I've got subpass info. And that's going to be a few things. Subpass index equals 0. Shader stages equals vert shader frag shader. Descriptors is empty. Vertex bindings is empty, and vertex attributes is empty. Okay. So you've got the subpass, and let's just call it subpass 0 for fun. And that's it. Now we just need to draw, and we know that our draw call is going to be like something like this. Because the draw is just going to be the same every frame. Cool. So we've got a draw, and we really just need some way of like from the renderer being like submit, and then I don't know, maybe it gives us some arguments, and then we declare like a render loop that's like submit a draw, like pure draw, and then loop. And then we'll be back to a working triangle example. So what we've got to do is implement this submit function. So this is kind of our last step. It's going to take a renderer, then a function that returns some draws, and then, yeah. Import that. Yes, so what would that look like? Probably finish soon, so probably won't get to do this today, but um, just give a taste of what that might look like. Uh, Definitely going to need to acquire the swap chain. Uh, let's list this out. So acquire swap chain. We'll get the next frame in flight. Get frame buffer for swap chain image. Allocate command buffers or buffer, and then record a draw. That's what we have to do next. I think we'll leave it here for today. My mind is so fuzzy. But yeah, that's where we're at. So yeah, I appreciate it's a little bit like half a step forward, two steps back, but I think it's going to be worth it in the end. Um, so yeah, thanks for watching and thanks for being here. And yeah, I hope that we can get somewhere with like pretty graphics and entertaining stuff soon. Um, so yeah, have a good day. See you guys.